In this lecture, we will learn about vectors and matrices. Vectors and matrices store a set of values, all of which have the same data type. A matrix is a table of elements. This could be a table of numbers or a table of characters. Each cell is called an element of the matrix. A matrix with a single cell is called a scalar value. A matrix that has a single row is called a row vector, and a matrix that has a single column is called a column vector. We can create row vectors in MATLAB using the square bracket notation, where the numbers are enclosed in square brackets and separated by commas. Commas are optional. You can also replace these commas with space characters. To create equally spaced numbers, you can use the colon operator, also called the iterator. And the syntax for using the colon operator is as follows. You would provide the lower bound, followed by a colon sign, followed by the step size, another colon sign, and followed by the upper limit of the numbers you would like to generate. In the first example, we are generating numbers from 1 to 5, with a step size of 1, so MATLAB will expand that expression into a row vector that contains numbers from 1 to 5. When the step size is 1, you don't have to write the step size, and MATLAB will expand this expression into the same row vector. In the third example, we have a step size of 2, so we will start from the lower bound, go 2 by 2, so we will get 1, 3, 5, 7, 9. Once you hit the upper bound, you will stop enumerating. So writing 1 step 2 all the way to 9 is equivalent to writing out this entire vector explicitly. Colon operator helps you write equally spaced numbers. In the next example, we are again generating a row vector with a step size of 2, but the upper bound in this case is number 6, so we will go 2 by 2, 1, 3, 5. The next number would be 7, which would be higher than the upper bound, so we will not go there, and we will stop at number 5. So this expression, 1 step size 2 all the way to 6, generates a row vector that contains numbers 1, 3, 5. It's also possible to have a negative step size. In that case, your first number will be 9, and again you will increment with this negative 2 amount. Effectively, you are decrementing the number by 2, so we will go 9, 7, 5, 3, 1, and once we hit 1, we will stop. We will not go any further than that. Sometimes instead of controlling the step size, you might wish to control the number of numbers you would like to have in your row vector. And you can use the linspace function to achieve that. To use the linspace function, the first argument would be the lower bound, the second argument would be the upper bound, and the last argument is the number of numbers you would like to generate. The first example, linspace, will generate numbers from 1 to 5, and you are requesting to generate 5 numbers. So MATLAB will effectively expand that to numbers 1 through 5. In the next example, you are generating numbers from 3 to 15. Again, you would like to have 5 numbers. So MATLAB will calculate the step size to fill in these numbers. And you can do that too. So the difference from 15 to 13 is 12. You have 4 increments, so each increment should be a step size of 3. So you will get 3, 6, 9, 12, 15. Concatenating vectors refers to putting together 2 or more vectors to make up a single vector. In the third example, we are creating a vector that contains another vector inside of it. And this will be expanded to a single row vector that contains numbers 3, 4, 5. So this expression is equivalent to the second expression that we have here. You can have vectors inside other vectors, and the variables will be expanded by their contents. So this is equivalent to writing the value of 1, which is 1, 2, and then the contents of B, which contains 3, 4, 5. Since we have row vectors inside a larger row vector, we are concatenating these row vectors, and effectively we are getting numbers 1 through 5. In the last example, we have variable A, variable B, followed by numbers 1, 2, 3. Variable A will be expanded with numbers 1 and 2. Variable B will be expanded with numbers 3, 4, 5. And then we have the numbers 1, 2, 3. When you have a vector in MATLAB, you would want to index individual elements of this variable. Indexing simply means accessing or referring to the elements of a vector. In this example, we have a vector V that contains 6 elements, which are numbers from 10 to 15. V sub 3 will get us the third element of this vector, and that will result in 12. The index can be a single number, such as V sub 3, or the index itself can be a vector, such as in this example, we are accessing the first, second, and third elements of the vector V, which will get us 10, 11, 12 as a new vector that contains 3 elements. When an indexed vector is on the right-hand side of an equal sign, you would be extracting the contents of that vector. When an indexed vector is on the left-hand side of an equal sign, you are writing the value that's on the right-hand side into this vector. In this example, we have V2 equals 30, which means you are writing the number 30 in the second box of this vector. So that will replace the number 11 with 30. When your vector contains only 6 elements and you are trying to write a value into the 20th element of the vector, MATLAB will automatically extend this vector to have 20 values, and it will store number 1000 in the 20th box and place zeros everywhere else, except that the first 6 elements which already existed will preserve the values that they had. This is called automatic extension, and it is recommended that you avoid automatic extension when you can, because it slows down your program. Now, there's a difference between storing into a non-existent entry, such as in this example, and reading from a non-existent entry. When you try to store into a non-existent entry, MATLAB will automatically extend your vector to have the appropriate size and store the number that you are trying to store in that element. But when you are trying to read a non-existent entry, MATLAB will complain and say that that entry does not exist. So whereas I can write V20 equals 1000, that is okay, that is valid, I cannot say V50 plus 6, because I'm trying to access V50, trying to extract its contents, which is not allowed because 50th box is non-existent. Let's work on this exercise and try to figure out what vector A will contain after each line of code. In the first statement, we are creating a vector that contains numbers from 2 to 8 with a step size of 2. So it will be a vector that contains 4 elements. In the next example, we are taking the number 33 and storing it in the 4th element of vector A. So vector A will still contain 2, 4, 6. Now the 4th element will become 33. In the next statement, we are taking number 11 and storing it in the 6th box of vector A. MATLAB will automatically extend vector A to contain 6 elements, and it will store number 11 in the 6th entry. The 5th entry, which was automatically created, will contain number 0. In the next statement, we are first extracting the contents of the vector A, and we are only taking the 3rd to the 6th elements. So that will contain from number 6 all the way to number 11. So it will contain the 3rd, 4th, 5th, and 6th elements of the vector A. We are extracting the contents into a new vector that will contain 6, 33, 0, 11. So that's the result of the right-hand side. And that result is then stored back in the variable A. So we are effectively replacing the contents of A, the entire contents of A. So A will no longer be this vector that contains 6 elements. It will now be a vector that contains only 4 elements, and those will be 6, 33, 0, and 11. In the next statement, on the right-hand side, we are concatenating the vector A, which now contains 6, 33, 0, and 11, with another vector that is composed of numbers from 4 to 12, and it only has 3 numbers. So that will be 4, 12. Since we have 3 numbers, we will only have 2 increments. We have a range of 8 to fill, and we only have 2 increments, so the step size will be 4. We are stepping 4 by 4, so the middle number will be 8. The concatenation of these 2 vectors will give us a new vector that contains 6, 33, 0, 11, 4, 8, 12. So that will be the result, which will be stored in variable A. Notice that if on the left-hand side I have an indexed A, I am only replacing the indexed elements. Whereas if I have A equals, I am replacing the entire variable A with whatever is on the right-hand side. Column vectors are very similar to row vectors. Instead of commas or spaces, you have to use semicolons to separate numbers. And again, we would be using square brackets to create column vectors. So this will create a column vector that contains 4 entries, and those will be numbers from 1 to 4. Another way to create column vectors is to first create a row vector, store it in a variable, and then take the transpose of this. So this vector R will be 1, 2, 3. It will be a row vector. Taking the transpose of this will make it into a column vector. I could also write out the vector 1, 2, 3 and then transpose it, store it in variable C. Instead of using an intermediate variable, I can directly take this vector and take the transpose. Now let's take a look at this tricky question. The incorrect answer for this exercise is that you might think that MATLAB will first expand the colon operator into a vector that contains 3 entries, 1, 2, 3, and then take the transpose, which would make it a column vector. But this answer is incorrect because of the operator precedence. The transpose operator is applied before the colon operator. So the way that MATLAB will interpret this expression is that it will first take 3 transposed. 3 is a single scalar number. So we have a single box. When we take the transpose of that, as a result, we will again get a single number 3. So 3 transpose will be replaced by 3. And then we would be applying the colon operator to get a row vector as a result that contains numbers 1, 2, 3. Matrices contain multiple rows and multiple columns. Again, we would be using square brackets to create matrices, and each row would be separated by semicolons. Within each row, we would have a row vector, and you can either use commas or separate your numbers with spaces. Another way to separate your rows is, instead of writing semicolons, you can just hit enter, go on to the new line, and start typing the next row. So both of these will give a matrix with 2 rows and 3 columns. So we have 4, 3, 1, 2, 5, 6. And the name of this matrix is variable M. When you are creating matrix variables, there is a rule that there must always be the same number of elements in each row. So each row should have the same number of columns. Let's look at the next example. The first row is a row vector that contains numbers 2, 3, 4. The next row is another row vector that contains numbers 3, 4, 5. When you are indexing matrices, again you would have parentheses, but inside the parentheses you would provide both the row number and the column number of the elements that you would like to index. In this example, M is a matrix with 2 rows and 3 columns, and it contains numbers 2, 3, 4 in the first row and 5, 6, 7 in the second row. M2, 3 is extracting the elements in the second row and the third column. So that will be this box right here, and that will contain number 7. So M2, 3 will be replaced with number 7. Similar to vectors, instead of using single numbers for indexing, you can have an array of numbers. In that case, you would be extracting multiple elements from this matrix. So in this example, we are interested in extracting the first row and the second row. So we will be referring to both of these rows. And we are only extracting the second column and the third column. So that will give us this portion of the matrix, which itself will be another matrix. So by using this expression, we are extracting a 2 by 2 matrix out of M, and that will contain 3, 4, 6, 7. There's a special notation in indexing, and that is the colon operator. Instead of a number or a vector of numbers, you can have just a colon. And when you have just a colon, it will pick all of the rows or all of the columns depending on which side of the comma you have your colon in. 2, 3, 4, 5, 6, 7. M1, colon will pick the first row and all columns, and it will give us a row vector that contains numbers 2, 3, 4. The next example is picking the second column and all rows, and it will give us a column vector that contains 3 and 6. In the last example, we see another special keyword, AND. AND will be replaced with the number of rows if it is on the left-hand side, or the number of columns if it's on the right-hand side of the comma. So in this case, since variable m contains only 2 rows, this is equivalent to saying m2, 2. Notice that I replaced the AND keyword with the number of rows I have in the variable m, which is 2. And then we had a comma 1. 2 colon 2 will generate a vector that has a single number 2. So that is equivalent to saying m2, 1, which will get me the boxes in the second row and in the first column. Second row, first column, and there's only one box there, which is 5. So that will give me number 5. I told you that when you are indexing matrices, you would need to provide the row number and the column number of the entries that you would like to extract. That is not very accurate. You can also index matrices using a single number. In this case, I have a matrix M, and when I retrieve M1 without any commas, that will get the first entry of the matrix. The way that MATLAB decides which one is first is by doing a column by column storage of the matrix. So let's take a look at this matrix. It's a 2 by 3 matrix that contains numbers 2, 3, 4, 5, 6, 7. In the computer memory, MATLAB will store this matrix in a linear order starting from the first column. So it will contain 2, 5, 3, 6, 4, 7. First the first column, then the second column, and then the third column. So the way that you write this matrix in the command window might be misleading. MATLAB, when it represents it in memory, it will represent it column by column, starting from the first column all the way to the last column. And then using this representation, you essentially have a column vector. So matrices can be represented as column vectors. And when you are using a single number for indexing, you are essentially using this column representation, and you would be performing indexing on this column vector instead of indexing on the original matrix. So with this new information, you can answer these 3 problems. M1 will retrieve the first entry, which is 2. So that will give us 2. M2 will get us the second element in the column vector representation of this matrix, which will be 5. The last example, notice that I do not have any commas in the indexing. When I had commas, the keyword AND would be replaced with the number of rows if it were on the left-hand side of the comma, and it would be replaced with the number of columns if it were on the right-hand side of the comma. When you don't have any commas, the AND keyword will be replaced with the number of elements in the matrix or in the vector. I have 6 elements in the vector, so saying AND is equivalent to just saying 6 for this matrix. So M6 minus 1 colon 6, and that's the same as saying M5 to 6. 5 to 6 will be a vector, so I am retrieving only the 5th and the 6th elements from this vector, and that will give me the values 4 and 7. In order to modify certain elements of a matrix, you would have your matrix variable on the left-hand side of an equal sign with appropriate indexing. In this example, we again have a matrix that has 2 rows and 3 columns. And in the first indexing example, we are referring to the first row and first column. So that's the top left corner, which contains number 2. And we are storing number 9 into it. So 2 will be replaced with 9. In the next example, we are indexing multiple elements of matrix M. We are referring to the first row and the first 2 columns. When you have multiple elements on the left-hand side, but only a single value on the right-hand side, MATLAB will take this value and distribute it into the elements on the left-hand side. So number 9 will be placed in the top left corner, which does not change its value because it's already 9, and also in the second box at the top row, and number 3 is now replaced with number 9. In the next example, we are again referring to the first row and first 2 columns, so we are referring to the same 2 boxes as the previous example. But now on the right-hand side of the equal sign, we have another vector, equals 1, 2. When you have an equal number of elements on the right and on the left-hand side of an equal sign, MATLAB will take the first element on the right and place it in the first element on the left, take the second element on the right and store it in the second element on the left. So number 1 will be placed in the first box that we are referring to. So top left corner will now become 1. And number 2 will be placed into the second box that we are referring to. The second number 9 now will become 2. Let me rewrite this matrix. We have 1, 2, 4, 5, 6, 7. In the next example, we are referring to the first row and all columns. So we are referring to the top row, which contain 3 elements. And we will be storing number 9 in each of these elements. So 1 will be replaced with 9, 2 will be replaced with 9, and 4 will be replaced with 9. The next example is an invalid expression in MATLAB because on the left-hand side we are trying to refer to 3 elements of the matrix, which is the top row, and right now it contains 999. And we are trying to store a vector that contains only 2 values, and MATLAB will complain that there's a mismatch between the right-hand side and the left-hand side of an equal sign. So this is an invalid expression in MATLAB for this matrix. In the last example, we are trying to store into the 5th row and all columns numbers 1 through 3. Similar to automatically extending vectors, matrix will also automatically extend matrices to accommodate additional writing. So the matrix, let's assume, is 2, 3, 4, 5, 6, 7. MATLAB will extend it to have 5 rows, and we will store into the 5th row values 1, 2, 3, and the result of automatic extension will put zeros where we have not stored any values in. When you have a matrix, you would often want to know the number of rows, the number of columns, and the number of elements it has. The function size will give you the number of rows and number of columns. Length will give you the larger of the two, and the number of elements will give you the number of entries in the matrix. In this example, we create a random matrix that contains 2 rows and 3 columns. Size m will return a vector, and this vector will have 2 values, number of rows and number of columns. You can store these 2 values in 2 variables called r and c. In this case, r will become 2 and c will become 3. Length m will return the larger of the number of rows or the number of columns. For this matrix, you will get 3. Number of elements will return 6 for this matrix, since we have 6 elements in this matrix. Let's work on this MATLAB exercise and create a matrix of zeros that has the same size as another matrix M. Let's solve this problem by writing a function. Let's call our function zeros by size. We will first write the function header. Out equals zeros by size m. We first want to identify the size of m, and let's store the size into variables r and c. So after that step, r will become the number of rows of m, and c will become number of columns in m. And we can use the values of r and c to create a matrix of zeros using the zeros function and providing r and c. And this function is done. Let's test it in MATLAB. Zeros by size. Let's provide a 2 by 2 matrix. Let's provide a 3 by 2 matrix. Let's provide a random 5 by 4 matrix. And you can see that it works in each of these cases. Another way to write this function is to directly provide the size of m to the zeros function. Zeros function is smart enough to handle the case where we provide a vector of 2 numbers that is returned from the size function, and it will create a matrix of zeros that has the same number of rows and the same number of columns. There are a number of functions in MATLAB that change the order of its elements or change the dimensions of the matrix. One of these functions is the reshape function. And let me illustrate it on this example matrix. It's a random matrix containing numbers from 1 to 10, and it is a 3 by 4 matrix. And I'll just make up some example values. When you are trying to figure out the result of a reshape function, I would recommend that you convert your matrix into the column-wise representation first. In the column-wise linear representation, we will store each column one by one. So first we will write down the first column, 186, then the second column, 923, then the next, 112, and then the last one, 375. Reshape takes the matrix that you would like to reshape, and then the number of rows and the number of columns that you would like to reshape this matrix into. In the first example, we are trying to reshape this matrix into a matrix that has 2 rows and 6 columns. So reshape will essentially take the linear representation of your matrix and fill in this new matrix column by column. So 1, 8, then 6, 9, followed by 2, 3, followed by 1, 1, followed by 2, 3, and followed by 7 and 5. And we get the result of reshaping matrix M into 2 rows and 6 columns. In the next example, we will be reshaping the matrix into 4 rows and 3 columns. Again, we will take the column vector representation and fill out this new matrix column-wise. So we get 1, 8, 6, 9 in the first column, and then 2, 3, 1, 1 in the second column, and 2, 3, 7, 5 in the last column. In the last reshape example, instead of providing a number of columns that we would like the new matrix to have, we are providing an empty vector that contains no values inside it. When you provide an empty vector to the reshape function, you are essentially asking it to calculate the number of columns required from the number of elements. Since we have 12 elements in our matrix, when you request the matrix to have 4 rows, MATLAB will automatically assume that you are trying to generate 3 columns, and it will give you the same result as the previous example. The flip LR function will take your matrix and flip it from left to right. So our matrix had 3 rows and 4 columns. As a result of flip LR, a new matrix will be returned, where this new matrix is obtained by switching the first column with the fourth column and also the second column with the third column. Flip up down will switch the rows from top to bottom. So it will take the first row and place it in the third row and vice versa. And since we have an odd number of rows, the second row will be the same in the matrix that is returned from the flip up-down function. Rotate 90 function takes your matrix and rotates it 90 degrees counterclockwise. So if our matrix had 3 rows and 4 columns, rotate 90 will rotate it counterclockwise, and as a result, the top right corner will now become the top left corner, and you will get a new matrix that is rotated. If you provide a second argument to the rotate 90 function, you can specify how many times you would like this rotation to happen. If you provide a negative number, then MATLAB will rotate in the clockwise direction. So in the last example, we are rotating twice in counterclockwise direction, and as a result, we will get this new matrix where the top right corner in the original matrix will now become the bottom left corner of the new matrix. Another useful function for working with matrices is repmat, which helps you replicate matrices. The first argument to this function is the matrix. The second argument is the number of times that you would like to replicate the matrix row-wise, and the last argument is the number of times you would like to replicate this matrix column-wise. Let's work on this example, which is a 2x2 matrix containing values 1, 2, 3, 4. In the first example, we will replicate once in the rows and 3 times in the columns. So you can think about this entire matrix as a single block. We are replicating only once in the rows, so we are not really changing the way that the rows are structured, but we will replicate this entire matrix 3 times in the columns, and we get the same matrix repeated 3 times. In the second example, we are replicating twice in the rows and twice in the columns. So as a result, we will have our matrix replicated twice in the rows and twice in the columns. And all of these submatrices will be identical to each other. And as a result, we will get one large matrix. In the last example, we are again replicating twice in the rows, but 3 times in the columns. So our matrix will be replicated 3 times along the columns and only twice along the rows. And each of these submatrices will again be identical to our original matrix. Most MATLAB functions can operate on matrices just as they would operate on scalar values. So ABS is a function that returns the absolute value of a number. If you provide a scalar value, a single number, it will just return the absolute value of that number. If you provided a vector or a matrix, in this example we are providing the vector of numbers from -3 all the way to +4, and it will return a new vector that contains the result of applying the ABS function to each of these entries. So it will contain 3, 2, and this is the result you will get. Likewise, the round function will apply rounding to each of the elements of the matrix that you provide. In this case, we are providing a random matrix that is 3 rows and 4 columns, and we are multiplying it by 10, so the random numbers become between 0 and 10, and then rounding them. So MATLAB will round each of the elements of this matrix and then return the result where you would be storing into the variable m. Sine function also supports taking a single scalar value. So if you say sine of pi, you will get 0 as a result. If you say sine of vector pi pi, then you will get a vector that contains 0, 0. Operators such as addition, subtraction, and multiplication support matrix operations. In this example, we have 2 matrices that are randomly generated and contain numbers from 1 to 10. Both of these matrices contain 3 rows and 4 columns. So that's matrix A, and let's have matrix B here. When you say A plus B, MATLAB will generate a new matrix that contains the addition of corresponding elements from A and B. So the summation of the first element will be placed in the top left corner. The summation of the first row's second columns will be placed in the corresponding entry of the resulting matrix, and this entire matrix will be filled in that fashion. A minus B will do the same thing, but instead of adding numbers, you would be subtracting corresponding numbers and filling out this resulting matrix. So addition and subtraction will perform element-wise addition and subtraction. However, when you try to multiply 2 matrices, by default, MATLAB will try to matrix multiply them. In matrix multiplication, you need to have the same number of columns in the first matrix as you have number of rows in the second matrix. So the first row of the first matrix will be multiplied element-wise with the first column of the second matrix, and the products of this multiplication will be added up, forming the top left corner of the resulting matrix. Matrix multiplication is the subject of linear algebra that I am not going to go into in this lecture. In our example, A matrix multiplied by B will be invalid since A does not contain the same number of columns as number of rows in B. In the last example, we have an element-wise multiplication operator. So if you have a dot multiply, that means element-wise multiply. And element-wise multiplication is very similar to the way that we did addition and subtraction. It will just take a look at the 2 matrices and multiply the corresponding entries from the 2 matrices to generate the resulting matrix. So the top left corner of the resulting matrix will contain multiplication of the two numbers from the top left corners of the original matrices. There's a special type of matrix in MATLAB called the empty vector. The size of an empty vector will be 0 by 0, since we have 0 rows and 0 columns. Likewise, the length and numeral functions will also return 0. Sometimes we may create matrices that have 0 rows and non-zero columns. This is useful, for instance, when we are trying to represent points in three-dimensional space, where we know for sure that the data should contain 3 columns, but we want to handle the case where we have 0 or more points. You can use an empty vector on the right-hand side of an equation to delete entries from a matrix. In this example, we have a matrix that has 3 rows and 4 columns. And in the first example, we are removing the 4th column from this matrix. So MATLAB will get rid of this 4th column, and as a result, M will contain 3 rows and 3 columns. In the next example, we are removing the first row, so MATLAB will get rid of this first row, and matrix M will have 2 rows and 3 columns left. In the last example, we are using linear indexing to remove entries from the matrix. This is allowed but not recommended. As soon as you use linear indexed deletion, MATLAB will convert the matrix to column-wise representation, delete the requested elements, and your matrix will remain as a column vector. So far, when we talked about matrices in MATLAB, we talked about them as two-dimensional matrices. But you can also have three-dimensional matrices in MATLAB. The way to think about three-dimensional matrices is to think about the third dimension as the number of pages in a book. So in this example, we are creating a matrix of zeros that has 3 rows and 3 columns and 2 pages. So our three-dimensional book will contain 2 pages, where on the first page we will have a 3 by 3 matrix, and on the second page we will have another 3 by 3 matrix. In the next line of code, we are generating a random 3 by 3 matrix that contains numbers from 1 to 10 and storing it in the first page of this matrix M. So this 3 by 3 matrix will be filled with random numbers. In the last line of code, we are again generating a 3 by 3 matrix of numbers that are between 1 and 10 and storing it in the second page of this matrix M and filling in the 3 by 3 matrix that's on the second page. Now let's solve these problems. In the first problem, we are asked to find an efficient way. Efficient meaning we don't want to write too much. We want to be lazy in writing, but not so lazy in thinking. And we want to generate this matrix M. So take a minute to try this on your own. If you look at the top row, it contains numbers from 7 to 10 with increments of 1. So we can write it as 7:10. And the second row contains numbers from 12 to 6 with a step size of -2. So that is 12, step size -2, all the way to 6. And to generate this in MATLAB, we would say M equals, open brackets, 7:10, semicolon, to indicate we are moving to the next row, and then 12:-2:6. You can take a minute to solve the next problem. One way to solve it is to add to M a matrix that has 1s in the first row and 2s in the second row, and this matrix should have the same size as M, MATLAB will perform element-wise addition to generate a new matrix that has the same size and contains addition of the corresponding values from these two matrices. So the solution to this problem is to say M equals M plus 1, 1, 1, 1, semicolon, 2, 2, 2, 2. Even though this is correct, it's not the best answer. The less you can write to answer a problem, the better. So let's try to find a way to write this second matrix in a more efficient way. We can use the wrapmat function for this purpose. If you look at the matrix that contains all 1s in the first row and all 2s in the second row, you can see that it can be generated by replicating a single column 4 times. So what we will do is say wrapmat 1 semicolon 2, comma, replicate once row-wise and 4 times column-wise, and then add that to M, say M equals M plus wrapmat. It's not much fun to look at numbers all day. You really need to plot your data to make sense of it. There's a function in MATLAB called plot that takes a vector x and a vector y, and it will generate a plot x versus y. In the third argument, you can specify the color of the line and the marker type being used. You can specify the axis for this plot. For instance, you can change the range of the x-axis to go from -1000 to +1000. X label will place a label for the x-axis. Y label will place a label for the y-axis. The title command will place a title to your plot. Grid on will turn on the grid for this plot. Whenever you call the plot function, it will remove the old plot and start from a fresh new plot. If you want to keep your previous plot in the figure, you would say hold on, and then next time you plot, it will plot on top of the previous plot. You can save your plots as image files by following the File menu and going into Save As. And then, for instance, you can take those image files and place them in your presentations or reports. In this exercise, we will be drawing random triangles using the plot function. To draw a triangle, we need to specify 3 points: A, B, and C. Plot function works by drawing lines. We want to have the plot function start from point A and go to point B. Let's say point A has coordinates x1, y1, and point B has coordinates x2, y2. If you want the plot function to go from point A to point B, you need to provide the coordinates of A and then the coordinates of B. From point B, we want the plot function to move to point C, and let's say point C has coordinates x3, y3, so the next point will be x3, y3, and then from there we want the plot function to go back to point A, which has the coordinates x1, y1. So our x vector will be x1, x2, x3, and then back to x1. Our y vector will be y1, y2, y3, back to y1. Once we obtain these two vectors, we can call the plot function and it will draw our triangle. We can provide additional arguments to specify the color, marker, and line type for each of these triangles. Now let's do this in MATLAB. I'm going to write a script named random triangles. And since it's a script, I don't need to write the function header. Let's create a random variable x that has 1 row and 3 columns. So this will contain the x coordinates of the 3 points. Similarly, y will contain the y coordinates of the 3 points. Remember that I had to go back from the third point to the first point. So to achieve that, I will just say x4 equals x1, which will store the x coordinate of the first point as the fourth entry of x. Let's do the same for the y vector. Now x and y will contain 4 values each, where the fourth value will be the same as their first value. Now I can call the plot function with x and y, and let's execute this function by clicking on this run icon, or on Windows you can also hit F5 key, and MATLAB will generate this figure. Let's dock this figure by clicking on this arrow key on the top right corner of this window to make it docked into the MATLAB window. Another way to execute this script is by typing its name in the command window, and every time you execute it, it will generate a new random triangle. Let's go into the script and follow its execution step by step. But first, let's clear all the variables from the workspace by right-clicking on them and saying delete. Let's run this script again, random triangles, and you can see that the execution stopped at the first line. You can step to the next line. On Windows, you can do this by hitting F10 or clicking on the step icon in the toolbar. So let's hit F10, and you can see that there's a new x variable in the workspace that contains 3 random numbers. Similarly, when we run the next line, we will get the y variable. Executing the next line of code, increase the size of x to contain 4 values, where the fourth value is now the same as the first one, and then executing the last line of code will generate a new plot. Let's try to simplify this script and only create a single variable a that will be a matrix that contains 2 rows and 3 columns. Now I can say the fourth column of A equals the first column of A. So instead of using 2 variables x and y as 2 separate vectors, I'm combining them into a single matrix A, where A is a 2 by 3 matrix. So I can remove all of this since A will contain all the information I need. And when I'm calling the plot function, I will provide the first row of A as the x argument and the second row of A as the y coordinates. I'm going to execute this by hitting F5, and every time I hit F5, MATLAB will plot a new random triangle by executing this script. The question also asked us to change the color and the line type of this triangle. For that, let's look at the documentation for plot. So DOC space plot will open this documentation window, and let's look at some of the examples. The third argument, there are some variations for it. Let's try one of them. So the letter R stands for color red, and star will be a star marker. Let's hit F5 and see how the triangle is now plotted. As you can see, it gets rid of the lines. I also need to provide a line specifier. Let's use a single dash and re-execute this line of code. Let's change this to 2 dashes. Let's replace it with a dot. Apparently dot is not a valid line specifier. Let's replace it with dash dot. And you can see different variations. We can change the color from red to blue. The question was asking us to generate 4 different graphs. So let's copy and paste this code 4 times. and each time let's change the way that the line is drawn. S stands for a square. Let's make the third one green, and let's use a diamond. And for the fourth one, let's use a circle as the marker type. And I'm going to hit F5 again to execute this function, and as you can see, only the last one is being shown. So what I'm missing here is that every time the plot function is called, it wipes off the results from the previous plots and starts from a fresh new figure. So in between these different plot function calls, I need to say hold on. And if I say hold on at least once, it will keep holding it until the end. And when I'm done plotting everything, I can say hold off. And every time I hit F5, you see 4 random plots being drawn on the figure. The last function that I would like to introduce in this lecture is the bar function that lets you plot bar plots. Let's look at the documentation for bar, and you will see some examples at the bottom of this documentation page, which may be too complicated at this point. Let's just run a simple example. We will make a bar plot from the vector x, which contained the x coordinates of the 3 points, and the fourth point had the same value as the first point, and you can see that they have the same height.